In last week's lecture, we started to talk about complexity studies, and we are trying to connect the ideas and concepts of complexity with those of systems thinking. In complexity studies, and in the readings you should have read by now, it's clear that there are two related concepts. One is chaos, and the other is complexity. And last week we discussed and gave examples of what chaos is. We go on now from where we stopped in chaos. We talked about chaos in time and chaos in space. When somebody mentions chaos in time, what should you remember? What's the idea to remember when chaos in time is mentioned? What's the key idea? Yes, the key idea is sensitivity to initial conditions. When initial conditions are just a little bit different, the trajectory that the system will follow in time will diverge from all the other trajectories which start at a different, from a different point. The other idea of chaos is chaos in space. And what's the key idea of chaos in space? What's the underlying feature of chaos in space? These are entities in space which do not become simpler when you divide them into parts. Okay, this is the idea of chaos in space. Where, in other words, where analysis, where calculus, etc., does not work. Okay, so these are the two ideas about chaos. Complexity, we said, implies chaos, but chaos can also occur in simple systems. That's another feature. People often confuse chaos and complexity. The confusion is understandable because most complex systems are chaotic in some region of the phase space. But not all chaotic systems are complex. For example, the three-body problem, we said that it's, the solution to the three-body problem cannot be obtained analytically because it is chaotic. It depends very much on the initial conditions. But the three-body problem is a simple problem, isn't it? It's not a complex problem. It's just three bodies revolving around each other. And we don't have all the attributes of complexity in the three-body problem. Yet it is chaotic. So all complexity often implies chaos, but the reverse is not always true. So let's go on to speak about these ideas, about complexity actually. Now, complex systems have several scales. Now, we know what scale and separation of scale is, so the idea is clear to us. We have discussed this in length. So all complex systems do have this property of having several scales. Now, the relation between chaos and complexity becomes apparent in this context. Chaos can be observed at a lower scale, but perhaps not at a higher scale above it. Again, we can understand this. For example, molecular motion is usually chaotic. And we gave the example of an engineer who is trying to design a bridge using materials like steel and concrete and maybe timber. And all these materials have molecular motion going on. So, in fact, the behavior of these particles can be chaotic, but the civil engineer is not concerned with this sort of difficulties. He looks at the situation at a higher level. He just uses average quantities rather than the exact locations of all the particles moving around in steel, for example. These averages could be the density of the steel, the ductile strength or the tensile strength, etc. So these average values at a higher level do not appear to be chaotic at all. So that's what it says here. Now, to understand complexity and its relation to chaos, we discuss Or remember the laws of thermodynamics. We are all familiar with these, but it is very useful to discuss these. Laws of thermodynamics are very fundamental to understanding the world. Not just for engineers, chemical engineers or mechanical engineers, or even for you, but for any educated person, understanding the laws of thermodynamics is essential, I think. So we just remind ourselves of these in these few slides. Everybody knows the first law. The first law of thermodynamics says that the total amount of energy remains unchanged in an isolated system. I did not define what an isolated system is. We know what an open and a closed system are. Okay. In science, the classification goes a little bit further than that. A closed system and an isolated system are differentiated, are thought to be different in science. An isolated system is what we understand as a closed system. There is no transfer of anything with the environment. No energy, no materials, nothing. So an isolated system is such a system. A closed system in science is assumed to be open to energy transfer, but not to material transfer. But these details are not too important for us. So isolated system, you understand, is a closed system as we understand it. So the total energy remains unchanged in a closed system. That's the first law. If there is a gradient means in science, the gradient means a difference, a differential. A gradient, you know the gradient vector, it's the vector of first differentials of a function. So a gradient in general is any difference. If there is a gradient such as a difference of pressure or temperature in the system, then this gradient can be used to do work, as we all know, okay? For example, if there is a difference of pressure in two chambers of gas, and if you open a window between the two chambers, gas in the high pressure area will flow into the low pressure area. And when during this flow, you can arrange so that something is moved or turned, so work is done. Okay? So we understand the concept of a gradient. But our ability to turn energy into work is reduced. That is, when gas flows from the high pressure area to the low pressure area, and when the transfer is finished, the energy is still there, but we can no longer use the gas to turn a wheel, for example, because the pressure has been equalized in both chambers. So we do work in an isolated system using part of the energy enclosed in the system, but the possibility of doing this sort of work will be reduced. For example, this is the same example. For example, we can do work when gas flows from a high pressure area to low pressure areas until there is no longer a pressure gradient. The pressure gradient becomes zero when it becomes equal everywhere. That is when the pressure gradient is reduced to zero and there's no possibility of using it to do mechanical work. When such a reduction takes place, we say that entropy has increased. Okay? The reduction in the possibility of using the energy to do useful work is called entropy. This is a very, very, very fundamental concept in science, entropy. Gas will not flow back on its own and separate itself into high and low pressure areas. It's the same with heat. For example, if you take two plates, one hot plate and a cold plate, and stick them together, you know that there will be a flow of heat from the high temperature hot plate to the low temperature cold plate. After a while, the temperature will equalize in both cases. But it will not be possible for heat to flow back on its own and separate itself into hot and cold areas. We all know this. In other words, spontaneous change is irreversible. Entropy always increases in an isolated system, and this is what we call the second law of thermodynamics. Energy is still there. There's no decrease in energy, but we cannot use it again. Only low entropy energy can be used. So now we can make a differentiation in the types of energy, calling energy as either low entropy or high entropy energy. Low entropy energy is useful because if entropy is low, there's the possibility of doing work, okay? High entropy energy is still energy, but we cannot use it to do work. So there's a quality for energy, as you can see. The quality will increase if it is a low entropy. So this is called, sometimes we can call it grade. The types of energy, therefore, will have different grades. The highest grade of energy, the perfect grade of energy, is electricity. Why is electricity of the highest grade possible? Why do you think electricity? I mean, by electricity, we mean electricity that you can use from the socket, from the wall outlet. Why is it of the highest grade? For example, you can compare it to petrol, or you can compare it to any wind energy or whatever. Why do you think electricity is of the highest grade? The grade of energy is to do with its ability to do work, you remember, with its being low entropy. Yes, why is electricity of the highest grade? Well, because you can do maybe 98% of electricity can be converted into work. You know, you have some idea of an electrical motor, huh? Electrical motors are very efficient. Their efficiency is above 95, 96%. So you can use the electricity and you lose only a few percent of it. You can convert almost all of it to work. So that's why we call electricity as the energy of the highest grade. Now, let's extend this idea of useful energy compared to energy not so useful. The maximum amount of work that a subsystem can do on its surroundings, I don't know why I wrote subsystem, it could be system, that a system can do on its surroundings is defined as exergy. Now, this is a concept maybe you haven't heard of. This is another physical concept, exergy. It's not as old as energy, but obviously. It is the component of energy that can do useful work. This is not an exact definition. Actually, exergy is more complicated than this, but we can understand exergy as such. It's the energy which can do useful work. That's fair enough for us. Now, there are 4 types of such exergy. There's kinetic exergy associated with relative motion. You know, you are familiar with kinetic energy. The amount of energy, kinetic energy, that can be used to do useful work is called kinetic exergy. Okay? Potential field exergy, this is associated with gravitational or electromagnetic fields. If you have an electromagnetic field gradient, that is, the charge in one area of a conductor is higher than the charge in the other area of the conductor, there will be current flow, electricity will flow. This is because of the potential field exergy. You know, this is measured by voltage, by electromotive force or voltage difference. Similarly, there's gravitational field. I mean, if, for example, I let this pen down, it will fall on the ground, it will do work, it will travel a distance because of the pull of gravity. But when it falls on the ground, it will not come back up to the table. The energy is still there, but I cannot use it to bring it back, to bring the pen back. There's physical exergy associated with pressure or temperature gradients. And finally, there's chemical exergy associated with chemical gradients. For example, the energy in oil, energy in gas, in natural gas, etc., are chemical exergy or chemical energy. And the useful part is called chemical exergy. Now, exergy is non-zero when the system under consideration is distinguishable from its environment. This is very, very important for us, the idea of distinguishability. distinguishable means distinct, that you can differentiate it from its surroundings. In one or more of these 4 dimensions, these 4 exergy dimensions. Therefore, exergy is the most general measure of distance from thermodynamic equilibrium or of the degree of distinguishability. Now, I should have underlined thermodynamic equilibrium. Also, thermodynamic equilibrium in an isolated system is a state of maximum what? Entropy, maximum entropy. In such a system, there is no possibility of doing any useful work. What happens is that you can assume that if you think in terms of the gas chambers, the neighboring gas chambers with a pressure gradient, when you let them mix together, the gas molecules will be distributed in both chambers uniformly. The pressure in each location will be the same as every other location. So it will not be possible to distinguish one area from any other area because they have all the same, they are all under the same pressure. When such a system settles down, when gas is distributed uniformly, we say that when also, for example, the temperature is also distributed uniformly, then we can say that the isolated system is under thermodynamic equilibrium. Under thermodynamic equilibrium, useful work cannot be done. Now, the second law says that all isolated systems are subject to increases in entropy, so that what will happen, according to this second law, in the end, after maybe billions and billions of years, all the universe will reach thermodynamic equilibrium. All the stars will burn out. There will be no temperature gradients left in the universe. There will be no pressure gradients left. There will be no gradients left, actually. And that is called the state of thermodynamic equilibrium. It's also called the heat death of the universe. Isıl ölümü, kainatın ısıl ölümü. So the idea of thermodynamic equilibrium is a state of death, actually. You can just use this sort of metaphor. In such a case, it is impossible to distinguish any region from any other region, so that the system becomes like a soup, if the metaphor is correct. You cannot make any distinction of the elements of the system. Now, exergy, therefore, if there is exergy, we are not yet at thermodynamic equilibrium. So exergy is a measure of distance from thermodynamic equilibrium. When exergy is 0, we are at thermodynamic equilibrium. Okay? Now, distinguishability here has the same sense as order, structure, differentiation, or as organization. All these terms can be used interchangeably for distinguishability. Now, thermodynamics is slowly coming up into our area of organization, order, and things like that. In OR, in operations, in industrial engineering, we are interested in organization. So the concept of organization, as you can see, is directly related to thermodynamics through this connection, with this connection. Differentiation being different. Structure, of course, we are using structure, the concept structure, more formally in systems thinking. By structure, we understand aspects that are subject to change, but very, very slow change compared to processes. But in everyday language, structure here is also used in place of order and organization. Entropy, on the other hand, is a measure of the degree of disorder of a system, its degree of indistinguishability or disorganization or lack of structure. let us just consider an organization from the social systems as a social system. An organization, for example, we have an organization here for educational purposes. We have this class. At some time, you all arrive at the class, and the lecturer comes in, and we have a lecture. That's an organization. You see, it makes it different from our surroundings. A political party is an organization. Members of a political party are different from all the rest of the population. There is a difference between an organization and its surroundings, in which there will be many, many other organizations probably. Some of these organizations will be overlapping for some members of the organization, etc. But there is this idea of being different. The state of maximum entropy, therefore, is a state of randomness. This randomness is also fundamental. It's important to understand this. Now, we can associate a link between thermodynamic equilibrium and uniform distribution. From statistics and probability, you are familiar with the uniform distribution. What is it? I mean, if it's a discrete uniform distribution, if you are talking about a discrete uniform, what's the other name for this? How can you express the same idea in everyday language? Equal likelihood. Equal likelihood. I mean, if it's a discrete distribution, for example, if I throw a coin and see whether heads or tails will result, this, for example, is if the coin is a fair coin. If it's a fair coin, then we know that it has this equal likelihood distribution. Both faces have equal chances of 0.5 probability of coming up. So uniform distribution actually implies randomness. Take any arbitrary enclosure or volume, unit volume in the gas chambers. The probability of a molecule being in that volume will be equal to the probability of being in any other volume. All volumes have the equal likelihood of containing a gas particle. This is what we mean by randomly distributed and uniformly distributed. So uniform distribution, random distribution is associated, therefore, conceptually with the state of thermodynamic equilibrium or maximum entropy. This idea is very, very general. For example, we defined exergy in terms of useful energy, but I said that the definition of exergy is actually more complicated than that. Why did I say that? Well, because, for example, let's think of some mineral ore, like iron ore, demir cevheri. Now, iron ore or coal carries energy, but iron, for example, iron ore does not carry useful energy. But let's just think of an iron ore located in some region in Turkey. Actually, there's exergy associated with the iron ore. Why? Because iron ore is concentrated in an area from which you can extract it and use it in your industry. If there were no exergy associated with the iron ore, what would you expect? The iron ore would be distributed randomly, in the entire geography. And it would not be possible to extract it. This random distribution, I mentioned the metaphor or the word soup, çorba dedik. And when a soup, of course, has particles in it, but just think of a soup which is clear, et suyu. When the universe becomes a soup, it won't be possible to identify the iron ore, or the coal ore, or the petrol, or whatever. So the idea of exergy is such a fundamental idea, or entropy and exergy. Uniform distribution, random distribution are directly associated with these ideas. that everything is distributed uniformly, so matter loses its properties of being identifiable. It just becomes, it's like the primordial gas from which the planets were formed after the Big Bang. Okay, this is so uniform distribution. Probability, randomness, maximum entropy is the second law, distinguishability, organization, character, etc. are all associated concepts. Now, open thermodynamic systems can maintain a state of disequilibrium. Disequilibrium as opposed to thermodynamic equilibrium. Which is more valuable for us? Obviously, a state of disequilibrium is essential for life. Okay? Under disequilibrium, it means that we have exergy and we can use it to do work. Now, open thermodynamic systems, and almost all thermodynamic systems are open in the end, maintain a state of disequilibrium by the transport of material and energy across their boundary. By feeding the system with material and energy, the system can be supported in a state of disequilibrium. Such systems are known as dissipative structures or dissipative systems. Now, dissipative systems, therefore, are open systems in our understanding in systems thinking, into which energy and materials and resources can be imported from the surroundings. And in this way, the system maintains itself. For example, electricity is fed into the room so that we can see each other and use this display. And I mean, if you are to stay here for a long time, food and water will have to be made available so that our meeting here, the class, can go on. Okay? Now, the concept of dissipative systems and dissipative structures was introduced quite lately in science, in the 1960s and 70s, actually. The name will be mentioned in a moment of the scientists who introduced these ideas. It's Prigogine. Dissipative systems dissipate gradients and maintain disequilibrium in a locally reduced entropy state. So a dissipative system, what is the thing that is dissipated? You know, dissipation is like spending, yani tüketmek demek, like consuming, dissipation. So what is being dissipated is the gradient. You can call it exergy also. Exergy, there will be no exergy unless there is a gradient. There must be some gradient. These gradients are dissipated, and therefore the system is maintained in a locally reduced entropy state. So an open system, the entropy of an open system can be reduced. The entropy of isolated systems will always increase. But in the case of open systems, by the import of exergy from the environment, entropy can be reduced. Locally reduced. And why is it locally reduced? Because the total entropy is still increasing. What we are doing is that we are exporting some of our entropy to the environment. So the total entropy is still increasing, but locally in our open system, entropy has decreased at the expense of the containing system. Is this clear? Is it? Okay, I mean, if we import resources here, there will be less resources outside. If we import electricity and fuel into this room to maintain our state of disequilibrium, there will be less useful energy outside because the total amount of energy cannot change. So entropy will increase outside, okay? So that's why we say locally reduced. entropy cannot be reduced universally. It can only be reduced locally. This is done at the cost of increasing the entropy of the larger system in which the dissipative structure is located. Dissipative systems self-organize into structures that dissipate gradients. Hence, self-organization is one way to reduce gradients. Dissipation means reducing the gradients. And what happens is that this is actually very, very important. For this, Prigogine received the Nobel Prize in 1977 or something like that, not very long ago. He proved, he showed in laboratory tests, etc. For he received the Nobel Prize for chemistry. He showed that dissipative systems have this property of self-organization. Now, life itself can be viewed as a sophisticated dissipative structure away from equilibrium that has emerged to counter the gradient imposed by the sun. What is the most powerful gradient imposed on us? It is the heat coming from the sun, okay? That's the most powerful gradient imposed on the Earth. The idea here is, the Prigogine's idea, says that all systems are dissipative, and they dissipate gradients. This is the nature of material world. This is an attribute of the world. It's just like the high pressure gas spontaneously flowing into the low pressure area so as to equalize pressures. This is a fundamental behavior of nature. So every component of a system is trying to dissipate a gradient. Now, when the sunlight falls on Earth, it's a huge gradient. Actually, for example, each living person on the Earth uses energy. Do you know how much energy you use as a person? You use energy for breathing, for living, for keeping in life, for walking around. And in an industrial country like Turkey, in a modern country, you use transportation systems, you use lighting, illumination, several things. As an average, how much energy do you think you use? What? Kilocalories? No. Well, just think of an electrical motor, which is constantly turning, okay? You are like an electric motor of around 1.5 kilowatts to keep you alive. Every person, to keep every single person alive and doing its usual activities, whatever. It's as if an electric motor of about between 1.5 and 2 kilowatts of electric motor is constantly working. That's the energy you use. Compare this to the energy sent by the sun to the Earth. It is about 10,000 times as great as this. So the energy coming from the sun is more than 10,000 times as the energy we need to maintain our everyday lives. So there's a huge amount of energy coming in, a huge gradient. Now, most of this is reflected back into space. Some of this is absorbed by the oceans and by the Earth. But the ocean, the Earth, everything tries to dissipate this gradient. Or the behavior of the Earth can be described as trying to dissipate this gradient. How does the Earth do this? Well, it uses many things. For example, the air pressure becomes different in different regions of the Earth, and there are storms and winds. These storms and winds are one way of dissipating the sun's gradient. There's precipitation and rainfall, and there are rivers flowing. This is another way of dissipating the energy coming from the sun. But more interestingly, another way of dissipation has been discovered by nature. What is it? It is life, you see. Life depends on what's the most fundamental process of life? Photosynthesis, okay? Photosynthesis. All life depends on photosynthesis. Of course, before photosynthesis, there was life in the oceans, in single-cell beings, but later on, when plants developed, when life developed into plants, etc., these plants discovered to photosynthesize, through photosynthesis, to turn the sun's energy into food, into green material, food material. That's the fundamental substance on which life now depends. If someday scientists can synthesize photosynthesis, most of our problems will be solved. It's impossible to synthesize photosynthesis yet. I mean, we cannot emulate plants and take over from plants to produce food. But photosynthesis, for example, absorbs about 3 or 4% of this gradient. So life can be understood as another method of nature to dissipate a gradient. These are very, very powerful ideas, I think, and it's useful to spend some time on these. Now, let's come from thermodynamics to complexity. Complexity can be defined as the degree to which the system maintains a thermodynamic disequilibrium. The degree of thermodynamic disequilibrium can be defined as complexity. Now, this is the most general definition of complexity. Now, let's leave thermodynamics alone and discuss complexity in general. I'm going to follow Béranger. Did you read Béranger text? You have understood these thermodynamics ideas, etc., and chaos ideas, I think. Now I'm going to use again his definition of complexity. It's a very, very good reading, this Béranger article. A complex system will self-organize onto an attractor. Let's start like this. Béranger doesn't say this, probably, I don't remember. But anyway, we have mentioned the concept of an attractor. An attractor is a region in the phase space of a complex system, which is a special type of region. And for some reason, the chaotic system or the complex systems are chaotic, as I said, time and again return to these regions. These are not stable points. That is, we cannot guarantee that the system will always return to those points in the phase, to those states, let's say, in the phase region, in the phase space. But they are more privileged than other regions. They are more likely that the system will visit them again in the future than other regions. These are called attractors, strange attractors. A complex system will self-organize onto an attractor. You see, when Prigogine received his Nobel Prize, he did not prove these on living organisms. He proved these in chemical laboratories, in chemistry laboratories. The self-organization principle is so powerful, and also in biology. Then he wrote several books about truth, reality, and science. Prigogine. Prigogine was a Russian. His father was a chemical engineer in Russia. They emigrated to Europe, I think in the 1940s or something like that. And he became a citizen of Belgium. So he died in Brussels. He received the Nobel Prize in Belgium, but he was a Russian chemist. you can look up his books, for example, his books written for the general public about the concept of the universe and truth and reality are excellent reading. Belanger summarizes the properties of complex systems as follows. First of all, a complex system contains many constituents or many parts which interact non-linearly. Now, as you will see, most of these attributes, which I have numbered, this is number 1, are also common in systems thinking for systems. We have said a system is just remove the attribute complex. A system is a collection of constituents or parts that interact. But here, the interaction has to be nonlinear for complexity. Secondly, the constituents of a complex system are interdependent. That's a familiar idea to us. A complex system possesses a structure spanning several scales. You see, most of the attributes of complex system are actually the attributes of systems in general, as we have discussed them. But you see, it is better to think of systems in terms of complex systems all the time, because simple systems in which, for example, there are no scales, etc., are not of interest to industrial engineers. All systems that we deal with are social systems, as we said in the first lecture, and all social systems are complex because they are purposive systems. They include individuals with different goals, goal-seeking individuals, which will change all the time. So complexity is the rule and not the exception. A complex system is capable of emergent behavior, and we also know this. But let us stay a little longer on this concept of emergence in the context of complexity rather than in the context of systems. Emergence is the fundamental property of systems. Emergent behavior at a higher level of scale arises from lower levels of scale, although the mechanisms involved are not easy to understand. So emergence is always a result of an interplay between scales. One example I used to use in this class in earlier year is football, for example. Football is a system. There are 22 players, there's a ball, there are 2 goals, and there's a pitch, football field. These are the components of football, right? What is an emergent property of football? Can you give me an emergent property of the system football? Okay, but a better one, maybe a more interesting one. It's entertainment, isn't it? Or competition, or excitement. Competition is the best, probably. Now, none of these components, like the ball or the 2 goals or the football pitch or the players, have this property of competition. Competition emerges when all the parts come together in football, right? So competition occurs at a higher scale. Huh? For example, you are not one of the players, but you are a spectator, or you follow the National Football League from the media, etc. Then you are not interested in the pitch where the last game was played. You are not interested, you do not care about the qualities of the ball or the color of the ball or the color of the uniforms that the players are wearing, etc., etc. You are interested at a higher level at the competition, how many points has each game, each team has won, etc., etc. So these scales have to be different when emergence occurs. Emergence can be complex or simple, as we said. In the case of football, it is fairly complex. In the case of 3 bodies revolving around each other, emergence is simple. Just there are 3 bodies. So emergence can be complex or simple. Mostly, of course, we are interested in complex emergent properties. they will be lost to reduction. If we try to understand emergence by taking the system football apart, we won't be able to understand. It's like when we shall not be able to understand walking when you look at the brain, at the arms, at the legs of an organism. When the organism comes together, the emergent property of being able to walk emerges. Now, this is interesting. If all states were equally likely, then there would be no emergence. Right? If at the lower scale, think of the phase space of the system at the lower space, at the lower level. If all the states were equally likely, then clearly the system would be in thermodynamic equilibrium. There would then be no emergence. Right? So the ideas of thermodynamics are directly connected to the ideas of systems, as you can see. It appears that relatively few configurations are special or privileged in some way. These configurations are what we call attractors. The combination of structure and emergence leads to self-organization that occurs when emergent behavior creates new structure. So that's what we understand from self-organization. Through emergence, the structure is modified. That's what we understand. That's what we call self-organization. Complexity involves an interplay between chaos and non-chaos. This is again a powerful idea. I'm not very familiar with these ideas myself. These are ideas coming directly from physics and the sciences. But we can understand it. An interplay between chaos and non-chaos. While chaos may be going on a scale, the scale above it may not observe this chaos. We have given examples of this from building a bridge, constructing a bridge, where the molecular motion can be chaotic, but the design of the bridge takes place at a level where there is non-chaos. Complex systems, such as living organisms manage to modify their environments so as to operate as much as possible at the edge of chaos. This is where life tries to maintain itself, at the edge of chaos, the place where self-organization is most likely to occur. Okay, let's leave it here and continue tomorrow.